Well, thank you for bearing with us. I'm the last talk today. As I was introduced, my name is Dave Woollard, and I'm the CTO of a company called Standard AI. And what we do is actually study human movement in retail spaces. So our primary customer is a retailer, and they're interested in the performance of their retail space. How we do that is fundamentally by uh, tracking humans in 3D pose throughout the entire physical space. We do that visually via overhead cameras, so basic security camera setups. And then we generate stable 26 key pose tracks across all of the store footprint. And we normalize that into 3D space with store footprints. You can imagine that we actually see a lot of data as well. So not unlike Alessandro, who just spoke, we work in the millions of tracks data sets. So, to give you an idea of the scale, one of our customers in one of their stores sees 40,000 shoppers a day. So that's the kind of scale and statistics that we have access to. But today, we've started asking questions about how we could use that scale of data to influence not just our understanding of the physical space, but also in more fundamental ways about how humans move and human-human interactions as a potential for influencing how robots might navigate the same spaces. And so, if you look at this, example, you're probably familiar with a crowded train station. It was a topic of the last talk as well. Humans are actually really, really good at navigating these spaces, and we don't totally understand why. But it's not that any particular human is amazingly good at knowing what another human within that space is going to do in the next 30 seconds or 45 seconds. But somehow the movement overall is still legible. And so that was the sort of question that we started with, and it was an intuition that led to some of what I'm going to talk about today. So let me start with what are we predicting? I think, it was brought up a couple of different times today thematically, but, at a very short time intervals, a second into the future, things like constant velocity are actually not bad at that for what it's worth. I'm going to show something in a minute that backs up the same claim. At greater and greater time distances into the future, though, again, to also echo a lot of what other people have said today, this becomes probabilistic. And so, we're still measuring a world of probable outcomes in any of our predictive space. And so, what I'm going to share is maybe a little bit of a complementary perspective to just prediction. And that is to say that, even though in a lot of robotic navigation, you can think about it as a combination of goal setting and wayfinding and safety, as we move toward these larger scale data sets, we start to see that even if single trajectories are noisy and are difficult to predict, absolutely true. But then, are there population scale motion that is stable for the purposes of training, is stable for the purposes of guiding navigation? And, ultimately, what out of our data sets on human movement might be useful as we study human behavior to this community who's studying how robots might move within the same spaces. And so just to, again, kind of recenter on the claim, one of the things that we started by looking at was, is this stable? Is there structure to the uncertainty within our predictions? And so just, as I said, this is a very simple model that we put forward to just understand what we were looking at in terms of the data. This is about 1 million samples that we took, and we saw across those samples, even at two different shoppers, two different structures of the shopping experience with different fixtures, different layouts, different sizes, we still see a matched curve in terms of the unpredictability or the error rates as they grow in time of forward-looking projection, just using constant velocity. And so what I took away from this initial finding was that humans are unpredictable, but the structure of that unpredictability is stable. And that was the first sort of key that led us to think that maybe we should go further, right? And so, the next kind of step in this process for us was, when we're thinking about shared spaces, safety is obviously paramount, but, you also have freezing robot problems and all the literature that everybody here is way more familiar with than I am. I'm by virtue of largely being, a physicist with dabbling in human behavior. I don't deal with robots that much, but you all do. One of the things that we started with was, could we coordinate robots in the same way that humans use anticipation through what we think are structured motion patterns? And so we started with offline learning of exocentric data. So this is, again, overhead cameras. And we were looking for human-human trajectory interactions. And from that, we built what we call shared space motion priors. And then we put that into a very simple planner just as a cost function to understand, how does this influence the overall navigation structures? And so, the punchline of this paper, I'm going to be presenting at Roman this year, but it's basically this: the learned motion priors increase human clearance, path penalties remain relatively small, and local structure outperforms the global structure. What I mean by that, and that's maybe like the most interesting insight personally for me, was that we took this motion prior and we applied it in two different ways. The first was a local influence weighting, where we were just modifying the path of the robot when they became, into close proximity with other humans. And then we applied it more globally across the entire plan in a different weighting fashion. And what we found was that, if we were looking for proxies for safety, like clearance and passing function and things like that, they improved. But with a global parameter, if you used the global motion structure of the humans moving throughout this space too strongly, the robot ended up becoming distracted, essentially. They followed global flow patterns and they moved further away from the goaling. And so, I think human motion structure can guide navigation without constraining it, but, it also led us to, this first principle for how we wanted to apply this human motion data, which is to say, we called it the locality principle, that basically, I'll call it in terms of like three different versions of the planner: a baseline, a broad prior that applied this very aggressively, and then a lighter local prior that was just used as a coordination cue. And so what we found basically was that human structure could guide the navigation, but not dictate it if we judiciously applied the signal. And so it led us to yet another question, as often is the case when you start on a line of research. And the next question was, if human motion contains stable structure, does that motion encode the environment? What structure are we talking about in these trajectories, and how does that actually work? And so, one of the things that we kind of delved more deeply into in the sort of measurement theory and psychometrics world was, how do we define a behavior? And, I think even in the talks that I've seen throughout this entire conference, behavior can mean different things to different people. And so, definitions are always good, and what we're doing in our own work is to say that a behavior of a human is really something that exists in lane space, but they manifest behavioral attributes. And so you can think about a behavioral attribute as something you can measure. And so that's, things that we all talk about velocity and orientation and dwell and things like that. Those are all measurable phenomena, and they in turn can imply an underlying latent behavior. But sort of, one of the things that we struggle with a lot is the behaviors, especially sort of complex latent behaviors, are often underspecified in the sense that, so again, from a retail perspective, I'll use a retail example, browsing. And you can imagine a world, even in a sort of robotics example, right? Like a assistive support robotics or service robot scenario where you would want to know whether a human was browsing or whether they were confused, and that might inform how you would plan for robot movement. In an autonomous situation, you would want to assist confusion, but not necessarily browsing. It's a great idea. It's incredibly hard to start to define, well, what is browsing and what's the difference between browsing and confusion? And so there we actually, we've spent a lot of time, because this is, again, kind of the core of what we do as shoppers, on the, let's see, your left, you're going to see footage from one of our actual stores. This is a shopper. They're entering frame from the bottom. And then at the right, you've got what you're actually measuring, the trajectory data. And this is, again, sort of simplified. That's just a centroid. And then we're running a model in the background that's determining when and where someone is browsing. Or in this particular example, we use impression terminology, so similar to e-commerce, right? So that's, a non-trivial problem in its own right? Because if you think about what you can measure, is it velocity? Is it orientation? It may be a combination of those, certainly, but then how is that different or reactive within the environment? Like, if I'm browsing at an end cap at the end of an aisle, wide open space, maybe some people around me, I'll do that differently, and I might manifest differently than if I'm mid-aisle with a shopping cart. All of a sudden, everything that you can measure, the velocity, the orientation, those parameters will become very different. So you could sort of start with deterministic models, and certainly we did, but what we found quite quickly was that we missed large swaths of data, of browsing behaviors. And so in order to start to study that further, we basically started down a path of trying to understand behaviors representationally. How do we measure this in a meaningful way? And what are the pitfalls associated with techniques to do this? And so, I think a lot of people would start with indicator first approaches, and so similar to what I was just talking about with regard to, this deterministic model for browsing, I would think about it in terms of orientation and velocity and things like that, measurable parameters, and I would tune that and I would get something out of it, right? But then when we actually looked, one of the techniques that we ended up working on and researching was that we kind of flipped the order of operations. And we started by treating every trajectory as a time series, and we used change point detection to understand when the regime changed, but not necessarily what it was. And so by starting first with the change instead of the pattern, we were able to then take all the light segments, cluster them, and then only then after that process was complete, we could sample them, label them semantically, and start to understand that these clusters, despite very different characterizations from a measured attribute perspective, are actually the same underlying latent behavior. And so, this has implications to things like accessibility, for example. Not all, I think we're sort of, we need abstractions and simplifications. So humans tend to be fairly uniform in a lot of our models, but if someone's in a wheelchair, they're going to move and browse differently than if they are able-bodied. And so it's this technique actually allows us a very broad range of possibilities within kind of the extremely large data sets that we work with to understand how even small representation of different characteristics eventually emerged and can be correlated together into underlying latent behaviors. And so what does this have to do with navigation? Great question. And actually, I skipped ahead a little bit. Again, our key findings are essentially that if you don't choose wisely in an indicator first pattern, you're going to end up in a spot where only certain portions of the space that you're attempting to label are actually reachable. And what we saw was that there's actually, again, statistically meaningful misses in the data that we couldn't reach when we took an indicator first approach. And so that's why we started segmenting on time. But there's more on that paper, and we actually presented earlier this week, and happy to talk about it. In fact, the person who led that's also in the room. And so, if we think about this, if behavior depends on representation, then getting back to navigation, can navigational structure emerge from this behavior? So you're starting to kind of see, clearly there's pattern and structure. We deal with retail, and retail is very structured, right? So, whether you know it because of a map or whether you see it in the overlay and patterns of the trajectories, you can start to see the same structure emerge, whether you're looking at the human movement or whether you're looking at the underlying map. And so that led to, from this question of behaviors, could we eventually arrive at navigation structure? And so in this work, we essentially took this, again, raw trajectories, and we segmented each of those trajectories looking for browsing episodes. And then we co-located all the browsing episodes into nodes in a graph representation, and we called those shelf visits. And, the key thing that's really interesting out of this work is that we didn't start with the structure. We started with the movement. And so it was only after we placed those nodes onto the map that we understood that, in fact, that was a representation of popular shelves or distinct sort of destinations within the underlying geography of the store itself. And so, we think what's, kind of interesting out of this map is that it does lead to the broader sort of transition probabilities or the structure of the navigation that was missing from our local motion prior influence. So, the takeaway here is that you see that pattern, and it is compressible, or we have found it to be compressible into these spatial networks. And I think a lot of people have seen graphs today, super powerful representation, nothing new here from a graph structure perspective, but I think the temporal element and how we discovered the nodes, I think are particularly relevant. And so, it leads you to the next kind of question, though, and that is, if this is, something that's discernible in shopping, is it universal? Is that something that we see in other data sets? And so we took a look at a couple of the canonical data sets from literature. And in fact, it's not universal, punchline, but also we do still see a lot of the same localized interactions, regardless of the type of structure that might be enforced in the broader environment. And so we actually do see, examples within what you might consider largely unstructured data. The Plaza environment is, there's certainly some limited structure in terms of how people are entering that space, but then largely from there, it's really just interpersonal navigation, and we see that reflected in the data. But then if you take another example, you start to see some of the structure reemerged. So we used the same mining techniques that we used within retail, and we applied it to the hotel data set. And you are starting to see some graph structure appear using the same techniques. And so, I'm calling this essentially like mesoscale structure within this particular environment. It's not an unstructured plaza, and it's not the very rigid confined spaces of a retail environment. It's something in between, but we are seeing the same patterns emerge. And I think that's kind of the interesting takeaway. So, I think the, kind of broad point here is that, because we have store layouts, we can assign meaning, we can assign semantics, but we don't do it a priori. And by not doing it a priori, you have something that is universally applicable, even if the semantics are going to vary in the environment. And so putting it all together, we went back to our planner, and again, very simplistic planner, but we went back to our planner and we added both influence from the local motion, that's kind of the interpersonal navigation that we saw from a local motion prior, and this graph structure. And we saw that if you paired together both influences, you see locally coordinated movement, but that was also kind of globally consistent. And that really did produce a more human-like overall trajectory in comparison to the work that we had seen in human-human interaction. And so, what I would kind of take as a punchline to this work is motion priors capture how humans move, but then the navigation graph captures where that movement is organized. And that's sort of a sort of a summary slide. You've got kind of the dominance of the local interactions within the plaza scene. You see this sort of intermediate mesoscale within the hotel scene. And then as we look to our retail environments, that's really where the semantics of that retail graph start to really come into play. And so the relative value of the graph really does grow with the environmental organization. And so that kind of leads to a second principle. Locality was first, and then this is sort of what we're calling the separation principle, which is to say that local motion priors capture human-human coordination, but then navigation graphs capture environment-specific organizational principles. And coordination, we have found, is universal, but then environmental organization is environmentally dependent. And that encapsulation is actually kind of elegant in some ways because it allows us to recreate a graph per environment, but keep the sort of general notion of human interaction clean. So just, kind of to recap those two, locality principle, separation principle, and then the implications are basically that, I think when you have existing benchmarks that measure prediction accuracy, they're not really measuring whether agents can successfully coordinate. And so, I think we need benchmarks that evaluate these interaction constrained navigation scenes as a way to sort of test beyond just things like displacement and into more legibility. And that led us to this question: Can we evaluate structure-aware navigation? Is that something that we do? Apparently. So, with traditional prediction, you're essentially asking the question, where are people going? And with what we're calling interaction constrained navigation, you're asking the question, can agents coordinate? And so, one of the things that I think is a takeaway for us is that accurate prediction doesn't imply successful coordination. And, that led us to start to try to build and mine our own data for interesting navigation sets using humans as the inspiration for successful solutions to complex interaction problems. And so if I skip a little bit ahead, you can see This was our first attempt at that. We were looking at raw trajectories within one of our retail environments, and we did some scene mining. It was not unlike Alessandro's presentation. We did not use an LLM, but we were looking for kind of similar, interesting, constrained patterns, specifically where humans did things that were clearly inefficient in order to avoid complexity of interaction. And I think those ultimately became some of the more interesting scenes. And when we finally kind of got there, we eventually arrived at a benchmark that we consider, something that really tells us under these complex interaction constrained circumstances, can a human or a robot or an agent navigate that successfully? And so, that's what we're calling the EvenFlow benchmark. And that's something that we've made available publicly at this point. There's about 150 scenes mined from real data that we have. And so that's available at this point on Hugging Face. And so I'll show a link at the end. So I'm going to leave kind of with, what I would consider as proposed hierarchy of human navigation, if I might be so bold. For us, it starts with these behavioral attributes. These are the observable things. This is what we measure. We measure velocity, orientation, key points within the human frame. And then our level 2 is really around behaviors. How do we then infer behaviors? And again, behaviors for us are in the latent space. And then from behaviors, our level 3 is navigation structure, and we think that is emergent. And then finally, level 4 is really environmental structure for us. So what does the environmental impact change with regard to our own local interactions and our decisions globally about how to move through the space? And then, my kind of one more thing is that, the other thing that we're looking at a lot is, because we have now a lot of human data on how people navigated these scenes, we're able to sort of recreate the simulations, replay the data, but entirely with simulated agents. And, ultimately, one of the things that we see is that those simulations really do shift the overall statistical distributions of the patterns of structure that we're seeing. And so, I don't know, and I can't claim to say that this is the entirety of the simulation gap, but I think that it's an important sort of takeaway here that, if we're not capturing just the, local interactions, but also the global structure and that global map, then, our resulting agentic simulations are not really true. And the fidelity of the resulting navigation that we might plan for is affected by that. And so ultimately, that's at least as a sort of counterpoint, it's a sort of recipe, in my opinion, for some types of largely illegible actions in which robot behaviors are discernible as different from the global pattern. Okay. So with that, I promised a couple of downloads. The benchmark's available publicly right now. You can take a look at it. We have a broader research lab. Despite being from industry, we also kind of do a little bit double duty, and we have a lot of interesting data. To give you a flavor, a lot of the data represented here is about 2.5 million chopper trajectories that we're using across a couple of environments. But, we see that in the order of 1 month of operations with just one client. So there's a lot more data where that came from. And so, with that, happy to take questions, and also, if you are interested in taking a look at different aspects of our data sets or collaborating further, happy to do that as well. All right. Thank you.
Thank you so much. Any questions?
Okay.
So super interesting. I was wondering about the latent behavior that you're looking at. Is it so important? Because the behavior is, let's say, an underlying motivation that you try to recover from the trajectory. And I was wondering, because sometimes I go into a store and I'm still listening to my podcast, and then I first walk a little bit around to finish the podcast episode, and then I start shopping. I was wondering if this is, for example, closest to browsing, then wouldn't it be better to look at clusters of trajectories and not call it browsing or podcast finishing, but just as a cluster on its own?
Yeah, so it kind of goes. I think the question goes to the use of the underlying label, and so we actually we only labeled to understand post fact semantically what was going on. We didn't actually ever use the label as part of the classification itself, right? So I entirely agree that, in fact, the diversity of manifestations in and of itself was something that we struggled with for a really long time. And it was only really when we took a purely statistical and like kind of classical data mining approach first that we ever got anywhere. In fact, we're predominantly machine learning engineers, and so we wanted to take kind of classical approaches first, and we started by labeling a bunch of data. And I can assure you that there were rooms of people arguing for months about whether somebody in fact was browsing in that moment or not. And I'm actually presenting the work on how hard it was to get label agreement in the annual meeting of the Psychometric Society next month. So it turns out that labeling approaches are, well, we'll just call them problematic.
Yeah. Okay, thank you.